Tonight, we're going to explore one of the biggest misconceptions about the journey to Mars. Ask most people how long it takes to get there, and you'll probably hear the same answer. About 7 months. Technically that's true, but it's only half the story. 7 months is just the journey to Mars. Getting back is an entirely different challenge. The planets don't wait for astronauts to finish their mission, and they don't align themselves around human schedules. The window to return home is dictated by orbital mechanics, not by choice. A typical journey to Mars takes roughly 260 days before the first boot ever touches the surface. Then comes the hardest part, waiting. Waiting for Earth and Mars to move back into the right positions before a return journey is even possible. By the time the first crew finally arrives back on Earth, they won't have been gone for 7 months. They'll have been gone for roughly 2 to 3 years. By the end of tonight, you'll understand why the familiar 7-month figure tells only a small part of the story. How orbital mechanics, rocket physics, and even the speed of light quietly shape every Mars mission, and what spending years away from Earth would really mean for the first humans to make the journey. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. That 7-month figure is real, but it hides more than it reveals. The precise number is closer to 259 or 260 days, the one-way cruise time along the most fuel-efficient path we have, a looping trajectory called a Hohmann transfer. It works by launching at just the right moment and letting the spacecraft arc outward from Earth's orbit until it intersects Mars on the far side of the Sun. It is not a straight line. Nothing in orbital mechanics is. The craft coasts most of the way under gravity, burning fuel only at the beginning and the end. It is the slowest practical route and the cheapest in propellant, which is why, for the foreseeable future, it is the default, which means that by the time a crew actually reaches Mars, closer to 8.5 months have passed, nearly 3/4 of a calendar year. But here is where the number starts to get complicated. That 260-day figure describes exactly one thing. It describes the deep space cruise, the arc through emptiness between Earth's orbit and Mars's orbit. Nothing more. It does not include the months of training and preparation on the ground before departure. It does not include any time on the Martian surface. And it absolutely does not include the journey home. The 7-month answer, the one that circulates in headlines and conversations, covers only the middle portion of a journey with 2 other large pieces on either side of it. Think about what those 260 days actually look like from the inside. A crew of perhaps 4 to 6 people, a single vehicle, the same walls every morning, the same faces across the same table, no fresh air that has not been recycled and filtered through machinery, no ability to step outside without full life support equipment, and no real-time conversation with anyone on Earth. Radio signals at interplanetary distances take between 3 and 22 minutes to travel one way, depending on where the planets happen to be in their orbits. A question asked from the spacecraft might not receive an answer for 40 minutes or longer. That is not a communication delay. That is a fundamentally different relationship with the people back home. A crew in deep space is, in a very real operational sense, alone. 8.5 months of that. To put it in terms a person can feel, that is longer than a full academic year. It is one complete turn of the seasons, from one winter to the next. An astronaut who left Earth in January would arrive at Mars in late September or early October of the same year, having watched no sunrises that were not through a porthole, having set no foot on ground that was not a metal floor, and that is only the outbound leg. This is where the public framing of Mars travel quietly misleads. Not through dishonesty, through incompleteness. The 7-month number is accurate as far as it goes. The problem is how far it goes, which is not very far at all. It answers a specific narrow question about cruise duration and leaves the rest of the picture dark. The real question, for anyone seriously contemplating what it means to go to Mars, is not how long the cruise takes. The real question is how much of a life the whole undertaking consumes. That is a different question. It leads to different numbers, and those numbers are considerably larger than 7 months. We will build toward those numbers carefully, but even at this early point, the shape of the problem is visible. An astronaut who arrives at Mars after 260 days has not completed the mission. They have completed the first third of the travel, at most. The planets are already moving. Mars and Earth are drifting into new positions along their separate orbits around the Sun. The geometry that made the outbound window possible will not repeat for another 26 months. The crew cannot simply decide to come home when they are ready. The orbital clock runs on its own schedule, indifferent to preference or fatigue, or anything the crew might feel after 8.5 months of a recycled air cabin. That detail, the 26-month cycle between launch windows, is where the real shape of a Mars mission begins to emerge. It is not the 7 months that defines the commitment. It is what comes after. The surface stay, the wait for the window, the return cruise. The sum of those pieces is what an astronaut actually signs when they agree to go. The full number will come. For now, what matters is that the frame has shifted. 7 months was always the smallest slice of a much larger clock. The question worth asking is what the rest of that clock looks like. That answer is more revealing and more demanding than almost anyone expects. Start with the distance. It seems like a simple thing to know. You want to go somewhere, you look up how far it is, you plan accordingly. That instinct works fine on Earth. It does not work for Mars. The number that gets quoted most often is roughly 225 million kilometers, about 140 million miles. That figure shows up in textbooks, in news articles, in mission explainers. It sounds authoritative. It sounds like something you could build a plan around. But here is the problem with that number. It is an average, and Mars is never at the average distance on any real launch date. The rocket does not fly to average Mars. It flies to wherever Mars actually is on the day the mission leaves Earth. Those two things are not the same. Both planets are moving. That is the piece the average hides. Earth and Mars are each traveling along their own separate orbits around the Sun, at different speeds, tracing different paths, never locked in place relative to each other. On any given day, the gap between them depends entirely on where each planet happens to be in its own loop. Sometimes they are on the same side of the Sun, close to each other in their orbits. Sometimes they are on opposite sides of the Sun, as far apart as the geometry allows. And the difference between those two situations is not small. At the best possible alignment, when both planets happen to be on the same side of the Sun and near their closest points to each other, the center-to-center distance drops to roughly 56 million kilometers, about 34 to 35 million miles. That is the closest Mars ever gets. It does not happen often, and it does not last long. But when it does, that is the number. At the worst possible alignment, when the planets are on opposite sides of the Sun and near their farthest points from each other, the gap exceeds 250 million kilometers. In extreme cases, it can push past 400 million kilometers, more than 250 million miles. Think about what that means. Same two planets, same solar system. The distance between them can multiply by nearly 10, depending solely on which date you choose. Not slightly different, not a rounding error. Nearly an order of magnitude separating the best case from the worst case. The clearest way to feel that range is through light. Light travels at roughly 300 million meters per second, about 186,000 miles per second. It is the fastest thing in the universe. At that speed, light circles the entire Earth in about 1/10 of a second. That is so fast it reads as instantaneous. You flip a switch, light moves, the room is bright. There is no detectable delay. The scale of Earth is too small for the speed of light to feel like travel at all. Cross the gap to Mars, and that changes completely. At closest approach, roughly 54 to 56 million kilometers away, a radio signal traveling at the speed of light takes about 3 minutes to reach Mars. 3 minutes one way before any response can even begin traveling back. At the worst separation, more than 400 million kilometers, that one-way delay stretches to about 21 minutes. That is the same signal, the same physics, the same unchanging speed of light. Only the geometry changes, and the travel time goes from 3 minutes to 21. That range, 3 to 21 minutes, is not a technical footnote. It is a map of how much the solar system changes shape, depending on where you look. But here is where it gets strange. The variability does not just matter for communication. It governs the entire structure of a mission. The 7-month cruise figure, the one that gets quoted as though it were a physical constant, is not a constant at all. It is the product of a specific choice. A mission launched at the right moment, when the geometry is favorable and the trajectory can follow an efficient arc, can achieve a transit of roughly 259 to 260 days. That is the best case scenario under reasonable fuel constraints. Change the launch date, attempt the crossing when the planets are poorly aligned, and the mission either burns far more fuel fighting the geometry or simply takes much longer. Speed alone does not determine the travel time. Position does. This is why mission planners do not talk about sending a crew whenever the crew is ready. They talk about launch windows. A launch window is not a scheduling preference. It is the narrow stretch of time when the planetary alignment is favorable enough to make the mission possible under real constraints of fuel and trajectory. Miss the window and the next one does not open for another 26 months. The synodic period, the cycle of time it takes for Earth and Mars to return to roughly the same relative positions, runs close to 2 years and 2 months. That cycle does not bend for any budget, any crew readiness, or any human calendar. Personal schedules get tied to orbital mechanics the moment someone decides to go. The astronaut does not choose the departure date. The solar system does. There is a version of this that sounds abstract until you try to hold it. You might picture a spacecraft flying to a planet the way a car drives to a city. The city sits at a fixed point on a map. You calculate the distance, you drive the road, you arrive. But Mars is not a city on a map. It is a moving target tracing a 1.5-year long loop around the Sun. And Earth is a different moving target tracing its own shorter loop. And the only moment a mission is practical is the brief window when both loops happen to bring the planets into an arrangement the math can work with. The road changes every day. Some days it is manageable, some days it barely exists. All of that orbital complexity feeds forward into the surface stay, into the return window, into the total length of the mission. The distance is not just a number, it is the engine behind the entire structure. And the geometry that governs the distance has more to teach before the full picture comes into focus. The geometry has more to teach, but so does the flight log. Real missions have been making this trip for decades now, and they leave a record, not a theory, not a model, a record of actual spacecraft, built in actual decades, fired by actual rockets, arriving at an actual planet. And when you read that record, something becomes clear. The answer keeps coming back the same. Take Viking 1. NASA launched it in August of 1975. It reached Mars in June of 1976. That is roughly 10 months in transit. A different era of spaceflight. Different technology, different mission, different rocket design. 10 months. Move forward 36 years. Curiosity launched in November of 2011 and landed in August of 2012. About 8.5 months. A far more sophisticated spacecraft. A nuclear-powered rover the size of a small car. 8.5 months. InSight launched in May of 2018 and touchdown in November of 2018. 7 months. On July 30th, 2020, Perseverance left Earth. On February 18th, 2021, it landed in Jezero crater. 6.5 to 7 months. 4 missions. Spread across nearly 5 decades of spaceflight. Different eras, different rockets, different science payloads, different engineering philosophies. All of them land inside the same band. Not scattered across a wide range, not wildly different from one another. All of them fall between 6 months and 10 months. The band is not a preference. It is not an accident of any one mission's design. It is the physical shape of the problem itself, repeating every time humans have tried to solve it. The answer was stranger than expected. You might assume that what varies from mission to mission is the quality of the trajectory. A clever design gets you there faster. A cheaper design takes longer. And there is some truth to that, but the variation is narrower than instinct suggests. The laws of orbital mechanics keep pulling every trajectory back toward the same regime. 6 months on the fast end, 10 on the slow end. Chemical propulsion does not break out of that band. It has not broken out of that band in 5 decades of trying. That is not a range that invites creative optimization. That is a hard physical constraint that every mission has confirmed. But there is something deeper underneath this, and it takes a moment to see clearly. When people hear the figure of roughly 480 million kilometers for Perseverance's actual traveled path, they sometimes assume it is a mistake. The average Earth-Mars distance is around 225 million kilometers, a figure already covered. The closest approach is roughly 56 million kilometers. So how does a spacecraft end up traveling 480 million kilometers to reach Mars? That is more than 3 times the closest possible separation between the two planets. The answer is that the spacecraft is not flying between 2 dots. It is flying between 2 orbits. Think about what that means. Earth and Mars are not sitting still in space, waiting for a ship to cross the gap. They are both in continuous motion around the Sun. A spacecraft leaving Earth carries Earth's momentum, and it curves outward through the solar system on a long arc set by the Sun's gravity. The Sun does not pull the spacecraft off course. It defines the course entirely. The path is not a straight line extended from Earth to Mars. It is a curved arc that sweeps through a large portion of the inner solar system before it intersects Mars's orbit at the right moment. That curve is automatically, unavoidably longer than the instantaneous straight line distance between the 2 planets on the day of launch. Every time, by a large margin. Perseverance traveled 480 million kilometers in roughly 210 days. Do the arithmetic. That works out to an average speed of about 26 kilometers per second relative to the Sun. Call it 93,000 kilometers per hour. About 58,000 miles per hour. Now consider what that means. A long-haul airliner cruises at roughly 900 kilometers per hour. A commercial passenger jet, crossing an ocean, covering thousands of kilometers, is traveling at 900 kilometers per hour. Perseverance was moving more than 100 times faster. 100 times faster. And it still took 7 months. Not because the spacecraft was slow, because the solar system is that large and the path is that curved, and there is no shortcut through the geometry. The arc must be flown. The distance must be covered. The months accumulate regardless of how fast the ship is going, because the ship is crossing a gap that no amount of engineering instinct quite prepares you for. This is the fact that tends to resist absorption the first time it arrives. The mind that hears 100 times faster than an airliner forms an image of something streaking across the sky, something arriving quickly. The sensation of speed at that scale should feel like barely any time at all. But the solar system does not negotiate with intuition. Perseverance was screaming across the inner solar system at tens of thousands of miles per hour, and it still took more than 6 months to arrive. That figure, the 6 to 10 month band, is not going away. It is repeated across Viking and Curiosity and Insight and Perseverance. It will repeat for any mission using chemical propulsion to reach Mars on an efficient trajectory. It is the price the solar system charges, and every robotic mission sent so far has paid it. For an uncrewed rover, that price is paid quietly. The rover does not need to eat. It does not grow weaker. It does not experience the months passing. For a crew of human beings, the same bill arrives with consequences that compound over time. And those consequences have barely begun to be described. Those consequences begin the moment the crew arrives. The natural assumption is that arrival means the hardest part is over. 9 months of weightlessness, of recycled air, of a cabin that never changes. 9 months of watching Earth shrink in the rear viewport until it becomes just another point of light. Surely the journey ends when the ship touches down. Surely the clock resets. It does not reset. Here is where the orbital geometry reasserts itself. The crew has traveled to Mars in roughly 260 days. Earth, during those 260 days, has kept moving on its own orbit. It has traced out its own arc around the Sun. By the time the crew lands on Mars, Earth is no longer where it was when they left. It is somewhere else entirely, following its own curve at its own speed. And a return trip does not work simply by pointing the spacecraft back the way it came. The planets have to line up again. That alignment has to come back around, and it will not come back around quickly. The wait is not a matter of days. It is not a matter of a few weeks. The crew must remain at Mars for approximately 455 days, roughly 15 months, one full Martian year nearly, sitting on the surface or in orbit, waiting for Earth and Mars to reach a geometry that makes a return trajectory viable. That wait is not a malfunction. It is not a planning failure. It is the structure of the solar system, enforced. No amount of engineering or rocket power changes the position of the planets. So the full schedule looks like this. Roughly 260 days to reach Mars. Then roughly 455 days near or on the surface, waiting. Then roughly 260 days back. Add those together and the total comes to approximately 985 days. Just under 1,000 days. Not 14 months. Not the roughly doubled version of a 7-month one-way trip that intuition might suggest. Nearly 1,000 days. 2.5 to 2 and 8/10 years, depending on the exact windows used. Not 2 long flights stitched together. A biographical episode. The robotic missions offer a useful frame here. When InSight launched in May 2018 and landed in November 2018, the cruise lasted about 7 months. But InSight's primary surface mission ran for 1 full Martian year, roughly 687 Earth days. Close to 2 full Earth years. The cruise was, in the end, the briefest part of the story. InSight spent far more time on the surface, listening to Martian tremors and measuring the planet's interior, than it ever spent in transit. The spacecraft that people picture traveling to Mars is a craft in flight. But the reality is that most of the mission unfolds after the flight ends. The same proportion holds for a crewed expedition. The 260-day outbound cruise, extraordinary as it is only the opening movement. Think about what 985 days means in terms of a human life at home. When a crew departs for Mars, the people they leave behind begin living without them. Not waiting in the way you wait for someone to return from a long trip. Keeping their room the same, setting a place at the table. Living. Moving forward through time at the normal pace, because time does not slow down for anyone on Earth while the crew is away. In 985 days, a child who is starting the 2nd grade will be well into the 4th. A parent who was healthy at departure might face a diagnosis, a surgery, a recovery, without their son or daughter present. Friendships shift. Relationships that were strong before departure change their shape. The world turns, in the full literal sense, almost 3 times, and the crew cannot be there for any of it. Not in the ways that matter. The communication delay means that by the time a message from home arrives, the moment it describes has already passed. A birthday, a graduation, a quiet crisis. The crew receives the news days or weeks after the event, sends a reply, and waits again. The conversation does not flow. It accumulates in packets, each one already slightly out of date. The crew is not gone in the way a traveler is gone. They are present enough to know what they are missing, and absent enough to be unable to do anything about it. This is what the mission actually asks of a person. Not to endure a long flight, to consent to nearly 3 years of biographical interruption. Training and quarantine stretch the total commitment well beyond the 985 days of the mission itself. The body changes on the outbound cruise. It continues changing on the surface. It will need months of recovery after return. Career trajectories bend. Years of professional life get folded into a single mission. The person who comes back is not quite the person who left, and the world they return to has kept moving without them. Wait, that word, return, carries an assumption built in. The assumption that coming back is simply a matter of choosing to. That at some point during those 455 days on the surface, a crew member who changes their mind could simply board the spacecraft and come home. They cannot. The return window is fixed. The alignment of Earth and Mars that makes a viable return trajectory possible arrives on its own schedule, and that schedule does not flex for individual wishes or changing circumstances. The crew is there until the window opens. The 455-day surface stay is not an itinerary. It is an orbital lock. No mission planner sets it. The solar system does. That is the full shape of the question that tends to get compressed into the phrase, "How long does it take to get to Mars?" The phrase invites a simple number. One number, one answer, one clean fact. But the real question is different. It is not how many months a spacecraft needs to cross the gap. It is how much of a life a person is willing to reshape around two planets and the slow arithmetic of their orbits around the Sun. The answer to that question is nearly 3 years, including everything before and after the cruise. And for the crew members who will one day go, the reckoning with what that means is only beginning. That reckoning starts with a question that looks simple, but is not. Who is actually keeping the schedule? Not the mission planners, not the flight directors, not the engineers calculating propellant loads. They are all working within a schedule that was already set before any of them were born, set before any spacecraft was built, set by the motion of two planets that have been circling the Sun on their own separate tracks for billions of years. To understand why a Mars mission lasts nearly 3 years, you have to step back from the crew and the hardware and look at the geometry itself. Earth and Mars are both in orbit around the Sun. That much is familiar. But they orbit at different rates, on different paths, at different distances from the center. Earth completes one orbit in roughly a year. Mars takes about 687 days, close to 2 Earth years, to complete a single lap. Because the two planets are moving at different speeds on different tracks, their positions relative to each other are always shifting. Sometimes they are close, sometimes they are on opposite sides of the Sun. Most of the time they are somewhere in between, and the gap between them changes every single day. This produces a pattern. Because Earth laps Mars roughly once every 26 months, the relative geometry between the two planets repeats on that same rhythm. Every 26 months, the configuration comes back around to something resembling the last favorable alignment. Astronomers call this the synodic period, meaning the cycle time for the two planets to return to the same geometric relationship as seen from Earth. Think of it as a slow clock, a very slow clock, one that chimes only once every 26 months and only briefly before the window passes and the next chime is 2 years away. But the reality was different. Within that 26-month cycle, not all moments are created equal. Some windows are better than others. The geometry at some alignments produces a transfer trajectory that is relatively efficient and reasonably shaped. The geometry at other points in the cycle produces something far worse. If you launch at the wrong moment, you are not slightly penalized. You are dramatically penalized. The propellant cost climbs to numbers that make the mission either unaffordable or physically impossible with any rocket currently on the drawing board, or the trajectory curves so badly that the spacecraft arrives at Earth on the return leg moving at the wrong speed, aimed at the wrong angle. Either outcome is unacceptable. So planners do not choose windows from a range of roughly equivalent options. They work with what the geometry offers during the brief stretches when the offer is reasonable. This is the part that surprises most people. The assumption is that a powerful enough rocket could simply leave whenever the crew is ready. Push hard enough, burn enough fuel, and the departure date becomes a matter of engineering ambition rather than planetary position. That assumption is wrong. Not impractical. Wrong in the precise physical sense. The orbits set the schedule. The rocket only decides how hard you push against it. A larger engine buys a few weeks of flexibility, at most. It does not buy you the freedom to depart in a month that sits outside the synodic window. The geometry of the solar system does not yield to thrust. You can choose to leave at a bad moment. The physics will make you regret it, and the propellant budget will make it impossible before you even get to regret. So the departure date locks, and then the surface stay locks from the same principle. Imagine a crew landing on Mars after their outbound cruise. They have arrived. The transit is done. And from the very first day on the surface, a new clock is already running. Not a clock any crew member can pause or negotiate or override. It is the 26-month synodic cycle running its quiet course. Earth and Mars continuing to shift relative to each other. the geometry evolving day by day in its own indifferent way. The crew is waiting, whether they experience it as waiting or not, for the configuration to come back around to something that makes a return trajectory viable. That wait takes about 455 days, roughly 15 months, longer than the outbound cruise in either direction. And this is the consequence that changes the shape of the entire mission. In a standard Hohmann-style human mission, the surface stay is not just a component of the total time, it is the largest component. The crew spends more time on Mars than they spend traveling in either direction. The transit is the opening movement. The surface is where most of the mission actually lives. Let's think about what that means in terms of the overall architecture. Roughly 260 days out, roughly 455 days on the surface, roughly 260 days back. The surface stay is nearly twice as long as either cruise leg. For anyone who imagined the mission as two long flights with a productive interval between them, the arithmetic reframes it completely. The productive interval is not between the flights. The productive interval is the mission. The flights are the bookends. And the reason the surface stay is that long is not complexity of the science objectives. It is not the need to accomplish a sufficient return on the investment. It is not a schedule padded by cautious planners. It is the orbital geometry, enforced. The window for departure opens when it opens, no earlier. This is what the structural notes of this mission mean when they say the whole expedition is encoded in orbital motion before any engine fires. The outbound launch date is constrained by the synodic window. The surface stay is constrained by the same cycle, counting forward from landing until the next viable return alignment appears. The return departure date is constrained again by the window on that end. Stack those three legs together and you get roughly 985 days, just under 1,000, because that is what the pattern of 2 orbits, 2 speeds, and one 26-month cycle produces when you calculate it through. The rocket does not set this. The mission architecture does not set this. The solar system set it the day Earth and Mars settled into their respective orbits. What the rocket decides is how efficiently you can ride the pattern. A more capable propulsion system might shave weeks off a transit leg, or allow access to slightly less perfect windows within the broader synodic cycle, or offer a modest expansion of the acceptable departure range. But the pattern itself does not bend. The 26-month clock keeps running. The surface stay stays long. The total mission stays close to 1,000 days. This is the master constraint. Everything else in the mission timeline flows from here. Every planning decision about crew selection, training timelines, resupply strategy, communication infrastructure, and psychological preparation is downstream of the simple fact that 2 planets orbit the Sun at different speeds, and their geometry repeats on a 26-month cycle that no human agency created and no human agency can dissolve. The synodic period is the clock. It was running long before the first Mars mission was proposed, and it will be running long after the last one returns. The crews who go will live inside its rhythm, whether they think of it in those terms or not. And the implications of that rhythm do not stop with the calendar. They reach into the physics of the rocket itself, because even before biology enters the picture, even before the human body begins to matter, the laws of motion impose their own hard ceiling on how fast a spacecraft can reasonably travel. The orbital pattern sets the schedule, but the rocket has a say in what it can do within that schedule. And what it can do turns out to be more limited than most people assume. The question seems simple enough. Why not just build a bigger rocket and go faster? More thrust, more fuel, shorter trip? The logic feels obvious. That is when the pattern broke. The relationship between extra speed and extra propellant is not a gentle curve. It is exponential. And that changes everything. The governing math is called the rocket equation. The idea is straightforward. The only way a rocket can change its speed, what engineers call delta V, a measure of total velocity change available for the mission, is to throw mass out the back. You carry propellant. You burn it. The exhaust flies backward. The spacecraft pushes forward. 2 levers exist, and only 2. You can carry more propellant, or you can throw the propellant out faster, which means building a more energetic engine. The catch is in how those levers scale. For a small gain in speed, you need somewhat more propellant. That is manageable. For a large gain in speed, you need absurdly more propellant. The spacecraft does not grow smoothly. It balloons. Push hard enough, and the spacecraft becomes a giant tank with a tiny payload and capsule perched on top. The habitat where the crew actually lives shrinks toward an afterthought as the fuel required to accelerate and decelerate it becomes enormous. This is not an engineering failure, it is the shape of the equation itself. Now, look at the actual numbers for a Mars trip. Chemical rocket engines, the kind flying today, produce exhaust at roughly 3 to 4 kilometers per second. That is the raw power of the propellant. High-performance hydrogen-oxygen engines sit near the top of that range. It is a fixed ceiling set by chemistry. Burn a chemical fuel and you get a certain exhaust speed. No amount of engineering redesign crosses that limit. The atoms themselves set the ceiling. To leave Earth's gravity and inject a spacecraft onto a transfer trajectory toward Mars, the required velocity change is also roughly 3 to 4 kilometers per second. That burn happens from low Earth orbit. Then, the spacecraft coasts. Months later, arriving at Mars requires another velocity change, either slowing into Mars orbit or shaping an atmospheric entry. The return trip repeats the pattern in reverse, added up across the entire mission, and the total velocity budget a spacecraft must carry runs on the order of Earth's escape velocity. That is roughly 11.2 kilometers per second, about 25,000 miles per hour. That number is worth sitting with for a moment. It is approximately 30 times the muzzle velocity of a bullet from a handgun. The spacecraft is not crawling. It is moving at a speed that has no everyday equivalent, and yet the physics still demands months in transit. Here is why. The exhaust speed is the lever, and the lever is short. When the total velocity budget you need is roughly 3 to 4 times the exhaust speed of your engines, the propellant fraction required becomes punishing. Try to shave a month off the transit by departing on a faster, more aggressive trajectory, and the delta V required climbs. The rocket equation responds to that climb exponentially. What might seem like a modest speed increase demands doubling or tripling the propellant mass. That extra propellant itself needs to be accelerated, which requires more propellant to move it, which requires more propellant to move that. The spiral closes fast. But wait, there is a technique that helps. It is called the Hohmann effect. The physics behind it is precise. Burning propellant while already moving very fast, and while deep in a gravity well, delivers more useful energy per kilogram of propellant than burning that same propellant in empty deep space. The reason is that kinetic energy scales with the square of velocity. A burn made at high speed turns more of the chemical energy into spacecraft velocity than the same burn made at low speed. This is why trans-Mars injection burns are performed from low Earth orbit, rather than from farther out. Low Earth orbit speed is roughly 7.8 kilometers per second, about 17,500 miles per hour. Think of it the way you might think of pushing a swing. The push at the bottom of the arc, when the swing is moving fastest, sends it higher than the same push made when the swing is barely moving near the top. The same force, the same effort, but dramatically more effect because of when and where it is applied. A trans-Mars burn made at the low orbit perigee uses that same principle. The spacecraft is already moving fast and deep in Earth's gravity well. The burn at that moment is worth far more than an equivalent burn made hours later in open space. And Hohmann helps. It is a real and significant advantage. Mission designers exploit it deliberately, but it does not rewrite the ceiling. It is an optimization within the limits of the rocket equation, not an escape from them. The practical result is a band. At the slow, fuel-efficient end of what chemical propulsion can realistically deliver, the one-way transit runs close to 9 months. At the aggressive, high-energy end, in a particularly favorable launch window, the transit can compress to around 3 months. That 3-month figure is not easy. It demands a favorable window, a high-energy trajectory, and a significant mass penalty. The spacecraft is heavier at launch, the launch vehicle is larger, and the mission cost rises sharply. Below 3 months, the math turns prohibitive. The spacecraft does not simply grow, it transforms. The habitat shrinks, the fuel tanks expand. The ratio of propellant to everything else approaches a point where what you are launching is essentially a very large fuel delivery system, with a small human compartment barely surviving inside it. The crew is along for the ride in a machine built almost entirely for the purpose of accelerating and decelerating itself. There is another path around this. Instead of compressing the schedule by going faster, a mission architecture can split the cargo from the crew. Supplies, equipment, and consumables travel on slow, fuel-efficient trajectories launched ahead of the crew. The same orbital geometry that makes fast transits expensive makes slow transits cheap. A cargo ship sent on a long, low-energy arc to Mars costs a fraction of what a crewed sprint would cost in propellant. The crew then follows on the fastest chemically feasible trajectory, arriving to find supplies already waiting. Think of it as the difference between a slow freight barge and a fast passenger ferry on the same crossing. The barge leaves earlier and takes the long way around. The ferry follows quickly, knowing the cargo is already there. That split does not shrink the total mission clock by much. The surface stay and the return window are governed by orbital geometry, as we have already seen, but it changes what a crewed transit vehicle needs to carry and therefore what it needs to weigh. The crew travels lighter. The trip remains months long. The orbital lock remains in place. The rocket equation, not the mission planners, has set the floor. The conclusion the physics reaches is unambiguous, not impractical, not a matter of budget or engineering maturity. Unambiguous in the way physical laws are unambiguous. To go meaningfully faster than 3 months on a one-way Mars transit, you cannot simply build a bigger chemical rocket. You must change the kind of propulsion entirely. The exhaust speed that chemistry can produce has been reached. The lever will not extend further. And the exponential penalty for demanding more from it does not negotiate. The orbital pattern governs when you can go. The rocket equation governs how fast you can get there. Together, they describe a hard floor beneath the mission timeline. Everything above that floor is negotiable. Everything below it requires a different kind of engine. And the question of what that different engine might look like is where the story of transit time goes next. So what does that different engine look like, and what does it actually buy? The first serious candidate is nuclear thermal propulsion. The idea is not new. It is not speculative. It was studied in depth during the 1960s under programs like NERVA, and the physics behind it is well understood. The concept is straightforward. Instead of burning fuel and an oxidizer to create hot gas, you carry a nuclear reactor. You run liquid hydrogen through the reactor core, heat it to extreme temperatures, and expel it through a nozzle. No combustion, just heat, applied directly to the propellant. The result is an exhaust velocity roughly twice what chemistry can produce. Specific impulse, the measure of how much thrust you extract from each kilogram of propellant, roughly doubles as well. That matters more than it might sound. Because the rocket equation is exponential, doubling your exhaust speed does not merely give you twice as much speed for the same propellant. It gives you dramatically more delta V for the same propellant mass, or the same delta V for dramatically less propellant. Either way, the trade improves in your favor. For a Mars transit, the consequence is real. Aggressive but physically credible nuclear thermal trajectories bring the one-way cruise down to somewhere between 2 and 4 months. 2 months at the ambitious edge of the envelope, 4 months at the relaxed end. That range sits well below the 6 to 9 month chemical band, and it is not fantasy math. It is the rocket equation with better inputs. But something was wrong. The engineering challenges are not about understanding the physics. We understand the physics. The challenges are about building a reactor reliable enough to operate in the vacuum of space, under intense radiation bombardment and thermal cycling, for months at a stretch. And then there is the question of launching nuclear material through Earth's atmosphere on a rocket that, historically, has sometimes failed. Neither of these is an insoluble problem. Neither has been solved yet. The second candidate works on a different principle entirely. Electric propulsion, using ion thrusters or Hall effect thrusters, does not heat a propellant and expel it. It uses electricity from solar panels or a reactor, to ionize a gas and accelerate those ions to speeds of tens of kilometers per second. The exhaust velocity is not twice chemical, it is 5, 10, 20 times chemical. The specific impulse is extraordinary. So why are astronauts not already riding ion engines to Mars? Because thrust is tiny. The force these engines produce is small, vanishingly small. A typical ion thruster might push with the force of a sheet of paper resting on your palm. It is efficient in the extreme. It is slow in the extreme. A cargo spacecraft can run an ion thruster continuously for months, spiraling gradually outward from Earth orbit toward Mars orbit, and by the time it arrives, it will have used a fraction of the propellant a chemical engine would have required for the same trip. For cargo, this is excellent. For crew, it is the wrong architecture entirely. Astronauts cannot ride a slow spiral that takes a year or more. The radiation exposure keeps accumulating. The microgravity exposure keeps accumulating. The psychology of an even longer transit, compressing inward. And the power requirements are enormous. To drive ion thrusters capable of moving a crewed spacecraft at any reasonable rate, you need solar arrays the size of a city block or a nuclear reactor. The ion thruster family solves a real problem. It solves a cargo problem, not a crew problem. There is a third option that does not require a new engine type at all. High-energy chemical propulsion, the Starship-class architecture, with on-orbit refueling. The claims of 90 to 104-day transits are not pure marketing. The math behind them is real, under specific conditions. A favorable launch window, a higher energy trajectory, and a steeper arrival at Mars can bring a chemical vehicle inside that range. It works on paper. The cost is not trivial. More energy at departure means more propellant at departure. More propellant means a heavier vehicle leaving Earth orbit. Possibly several orbital refueling flights per mission, stacking propellant in low Earth orbit before the trans-Mars burn, and then the arrival. Higher speed at Mars means more kinetic energy to shed, more violent atmospheric heating, less margin between a controlled entry and a catastrophic one, thicker heat shields, more stress structures. That is not a free lunch. It is a compressed timeline purchased with compounding complexity at both ends of the trip. The arrival cost in particular deserves its own attention, and it will get it. Beyond these three families lies a frontier that is worth naming honestly. Fusion drives, light sails. The idea of a fusion engine is to fuse light atoms and expel the products at hundreds of kilometers per second. Exhaust velocities that would make nuclear thermal look slow. If you could sustain even continuous acceleration at roughly 1,000th of a gravity, about a tenth of a meter per second squared, the math becomes genuinely dramatic. You accelerate for the first half of the distance, flip the spacecraft, and decelerate for the second half. A trip that takes 7 months on a Hohmann transfer could shrink toward weeks. None of that exists at operational scale. There is no prototype fusion engine. There is no laser sail infrastructure anywhere near the scale required to push a crewed spacecraft. These ideas are not wrong. They are early. The gap between a promising physical concept and a working propulsion system is measured in decades, and in problems not yet encountered. But the reality was different from what these engine families seemed to promise. Even if a month-long Mars trip became possible, it is not obvious that you would want to push to the absolute minimum. Faster arrival means more kinetic energy arriving at Mars. More kinetic energy means more violent atmospheric entry, higher G-loads on the crew, higher peak heating on the vehicle, narrower margins between a successful landing and a catastrophic failure. The faster you arrive, the harder the problem of surviving arrival becomes. The practical sweet spot is not the physical minimum, it is probably somewhere near 3 to 4 months. Fast enough to meaningfully cut radiation exposure. Fast enough to shorten the psychological compression of deep space isolation. Slow enough that arrival remains a manageable engineering problem rather than a stunt performed at the edge of survivability. Nuclear thermal propulsion, or very high energy chemical with refueling, can reach that range. Pushing beyond it, toward 1 month or 2 weeks, begins trading human safety margins for numbers on a transit clock. Better engines bend the curve. They do not erase it. And what waits at the end of the curve? the problem of arriving intact at a planet with a thin atmosphere and a high-speed spacecraft, turns out to carry its own hard physics. But the hard physics of arrival is only one part of what waits at the end of that curve. There is another problem. And it does not live in the engines or the trajectory calculations or the heat shield specifications. It lives in the people inside the spacecraft. The moment a crew leaves Earth's magnetic field behind, a different set of clocks starts running. These clocks are not printed on any mission timeline. They do not care what the trajectory looks like on paper. They measure something else entirely. They measure damage. Space is not empty. Between the planets, high-energy particles stream in from every direction. Some come from the sun in sudden violent bursts. Some come from beyond the solar system altogether, accelerated by ancient stellar explosions across the galaxy. On Earth, the planet's magnetic field deflects most of these particles before they reach the surface. The atmosphere absorbs the rest. A person living on Earth for an entire lifetime accumulates a modest radiation dose, spread across decades, small enough that the body can manage and repair. In deep space, that protection is gone. There is no magnetic field. There is no atmosphere. Every particle that would have been bent aside or absorbed now passes straight through the spacecraft wall and through whatever is on the other side. Here is where it gets strange. Scientists measured the actual radiation dose during a real Mars transit. Not a simulation, not a model estimate. The Mars Science Laboratory, the mission that delivered the Curiosity rover to Mars, carried a radiation detector during its cruise phase. What it recorded was this. A one-way trip of several months to Mars delivered a dose that consumed a substantial fraction of what NASA considers an acceptable career total for a human astronaut. Not background noise, not a manageable exposure to be brushed aside, a significant fraction of a lifetime allowance, spent in a single transit. And the relationship is direct. Double the transit time, and you roughly double the dose. There is no way around the arithmetic. Longer cruise means more accumulated damage, more elevated cancer risk, more potential harm to organs and to the central nervous system. Shielding helps at the margins. A storm shelter, a small heavily shielded compartment for the sudden solar bursts, can reduce exposure during the worst events. But full shielding against galactic cosmic rays requires mass, a great deal of mass. And the rocket equation, which we have already met, makes clear that every kilogram of additional shielding is a kilogram that demands more propellant to carry, which demands more propellant to carry the propellant, and so on. The spacecraft cannot simply be wrapped in enough material to solve the problem. The physics of the rocket equation and the physics of radiation create a locked tension that no single engineering choice can resolve. Radiation alone pushes hard towards shorter transits. It is a soft deadline embedded in human biology. Stay in deep space long enough, and the mission becomes a medical liability regardless of how well everything else goes. But radiation is not the only clock that starts running. In weightlessness, the human skeleton begins to forget its own purpose. On Earth, bones are built and maintained by the constant mechanical stress of carrying weight. The skeleton is not passive architecture. It is a living tissue that rebuilds itself in response to load. Remove the load, and the body reads the situation as a signal that the bone is no longer needed at its current density. It begins to thin. Months of weightlessness in orbit produce measurable, quantifiable bone loss, particularly in the legs and spine. Muscle weakens by the same mechanism. The cardiovascular system, no longer fighting gravity to push blood up to the brain, adapts to its new environment. The heart shrinks slightly. Blood redistributes. The body becomes, in a real physiological sense, a creature of weightlessness. The International Space Station has been a laboratory for understanding exactly this process. Astronauts on 6-month missions exercise for roughly 2 hours every day, mandatory, using treadmills with harness systems and resistance machines designed specifically for this environment. They work hard at it, and when they return to Earth, they still require weeks of rehabilitation before they can walk normally. 6 months of dedicated physical effort against the effects of weightlessness, and the body still needs recovery time. The practical threshold is near 6 months. Beyond that, the accumulated damage to bone, muscle, and cardiovascular function grows harder to reverse. The body's adaptation deepens. The crew becomes more capable at zero gravity and less capable at any gravity at all. And here is the detail that makes this more than abstract. Mars does not offer full gravity. Mars' surface gravity is about 0.38 g, roughly a third of what the human body evolved to handle. A crew weakened by months of weightlessness does not arrive at a place where they can simply recover by standing up and walking around. They arrive at a partial gravity environment, not enough to reverse the adaptation, not enough to fully reload the skeleton, not enough to retrain the cardiovascular system quickly. They must perform their entire surface mission while still deconditioned from the flight. This matters for a transit band calculation. The 6-month comfort threshold is not an official regulatory limit. It is the practical upper boundary beyond which the compounding physiological costs begin to make the surface mission itself harder to perform safely. And then there is the third clock, the one that is harder to measure but not harder to feel. Think about the psychological architecture of a Mars mission. The outbound flight is months inside a pressurized volume, roughly the size of a large trailer. The same small group of people, no way to leave, no fresh air, no real privacy, no sky. Then the surface stay. Over a year in a habitat that is, by necessity, small, surrounded by an environment that is immediately lethal, with limited supplies, and with the knowledge that help is not coming in any meaningful time frame. Then another months-long return flight in the same kind of enclosed space. And throughout all of it, communication with Earth is delayed. At Mars distance, a signal takes somewhere between 3 and 21 minutes to arrive, depending on where the planets are in their orbits. A question does not receive an answer for half an hour or more. A conversation does not flow. It accumulates in packets, each one arriving already slightly out of date. A crew member experiencing a difficult moment cannot call a psychologist and talk through it in real time. A conflict between crew members cannot be mediated by ground support overnight. A small interpersonal friction that would dissolve quickly in normal life, where a person could simply leave the room and take a walk and see different people, has nowhere to go. It lives in the habitat. It has to be managed inside the same small pressurized space where everyone sleeps and works and eats and has been doing so for months already. Training helps, careful crew selection helps, but neither can remove multi-year confinement. They can only prepare people to endure it, as well as human beings are capable of enduring it. Longer transits make this worse in every dimension. More months in the initial confined flight. More months in the return flight. More total time before the crew sees Earth again and can decompress in the full sense of that word. Going faster would seem to solve all of this. Shorter transits mean less radiation, less bone loss, less psychological compression. But faster transit carries its own costs. Higher speed trajectories arrive at Mars with more kinetic energy. Entry into Mars's thin atmosphere at higher speeds means higher peak heating, higher G loads on the crew, narrower margins between successful landing and structural failure. Faster is not automatically better. The arrival problem grows with speed. There is a floor on how slow is safe. There is also a ceiling on how fast is survivable. What emerges from these overlapping constraints? Radiation, microgravity, psychology, and arrival physics together is a band. Not a preference, not a design choice, a biological and physical band where each threat is at an acceptable level, and none of them becomes disqualifying. That band sits near 3 to 6 months each way. Below 3 months, with near-term propulsion, the arrival stresses become extreme and the propellant demands become severe. Above 6 months, radiation accumulates into dangerous territory. Bone and muscle damage deepens past comfortable reversal, and psychological strain compounds beyond what training can reliably contain. 3 to 6 months each way. Add the roughly 500-day surface stay that orbital geometry requires. The total comes to somewhere between roughly 2 years at the optimistic end and 2.5 to 3 years at the more realistic end. Not because of poor planning, not because of budget limitations, because human bodies have finite tolerances and those tolerances overlap with the physics of the solar system to produce this specific window. The bottleneck is no longer only the rocket. It was always also the people the rocket carries. And those people carry biology that billions of years of evolution did not design for this. There is one more detail worth noting. Almost no data exists for what happens to a human body sustained at 0.38 g, the gravity waiting at the end of this journey. Earth offers 1 g. Orbit offers near zero. Mars offers something in between that no one has ever lived in for a year or more. The first crew to spend over 500 days on the Martian surface will be the first test case for that question. The answer is not yet known. The mission will produce it. Now follow the mission all the way to the ground. Those months of radiation and muscle loss and confinement end with something that engineers have given a name. They call it the 7 minutes of terror, not as a metaphor, as an accurate description of what the physics demands. Here is the problem. Mars has an atmosphere, not much of one. Surface pressure runs at roughly 1% of Earth's sea level pressure. That sounds almost negligible, but it is not negligible enough. It is just enough to heat a spacecraft violently if it arrives too fast or at too steep an angle. And it is far too thin to do what Earth's thick atmosphere does for returning capsules, gradually bleeding off speed across a long, gentle descent. Mars sits in a narrow band. Enough air to punish, not enough air to protect. Think about what that means in practice. Earth wraps itself in a dense atmospheric blanket. A spacecraft re-entering Earth's atmosphere has a long cushion to bleed off energy, spread the heating over time, decelerate gradually. Mars offers something closer to a whisper. The heating still happens. The deceleration still happens. But the window between too shallow and too steep, between not enough braking and too much heat, is narrow in a way that leaves almost no room for error. The robotic missions have already shown us what that window looks like. Curiosity and InSight both entered the Martian atmosphere at roughly 20,000 kilometers per hour, close to 12,500 miles per hour. From that speed, they decelerated to near zero in approximately 7 minutes. The sequence had to unfold in a specific order. Heat shield first, absorbing the initial thermal assault, then a supersonic parachute, deployed at the precise moment the air was dense enough to catch it. Then retro rockets, or, in Curiosity's case, a sky crane lowering the rover on cables in the final meters. Each step depended on the one before it. None of it could be corrected in real time from Earth. The signal delay alone meant mission controllers were watching events that had already concluded. The spacecraft was on its own. That sequence worked, but those were robots. A lost rover is a loss of equipment and years of work. It is not a loss of lives. For a crewed mission, every constraint multiplies. Peak deceleration forces must stay within what a human body can tolerate. Redundant systems must exist for each stage. Backup paths must be planned. The margins must be wider. And here is where the speed decision made weeks or months earlier comes back. A faster transit means arriving at Mars carrying more kinetic energy. That energy does not disappear at arrival. It has to go somewhere. It goes into heat and deceleration forces during entry. Every extra kilometer per second saved in transit reappears at arrival as extra thermal load on the heat shield. Extra G forces on the crew, narrower margins in an already narrow system. The week saved in cruise becomes a harder landing, not a minor complication, a fundamental coupling. The same transit speed that a mission designer might choose to reduce radiation exposure or shorten crew confinement shows up on the other end of the journey as a more violent entry profile. Speed and arrival are not independent decisions. They are the same decision, separated by months. This is why mission planners have considered an alternative. Instead of flying directly from Earth into the Martian atmosphere, a crewed spacecraft could first capture into Mars orbit. Enter orbit, verify all systems are functioning, confirm the landing site is clear, and then perform a separate, controlled descent. That approach allows far more oversight and far more opportunity to abort before the commitment of entry. But orbital capture is not free. It requires a significant propulsion burn, or a technique called aerocapture, which uses the upper atmosphere to slow the spacecraft into orbit, without a large burn, but which introduces its own thermal and guidance demands. Faster arrival means more energy to bleed off in that process too. The trajectory, the orbit versus direct decision, and the landing system design are locked together. Change one, and the others all shift. The practical consequence is this: crewed missions built around survivable entry profiles naturally converge on arrival speeds that their systems can handle. And those speeds correspond to transit times that push back toward the 6 to 7 month band. Not because the engineers prefer it, because the landing system sets a ceiling on how fast the spacecraft can safely arrive. And that ceiling, working backward through the trajectory, defines how fast the outbound crews can be. A saved week in transit should feel like pure gain, but that week does not vanish. It reappears at the other end as extra heat, extra force, extra complexity, at exactly the moment when complexity is least welcome. That is the arrival constraint, but the safety architecture does not stop there. Consider what happens if something goes seriously wrong in the middle of the cruise. Not a minor system fault, a major failure, an engine that will not restart, a life support problem that cannot be resolved. On Earth, or even in low Earth orbit, options exist. Crew can shelter, wait, be reached. In deep space between Earth and Mars, there is no pullover. There is no rescue mission that could arrive in time. The only safety net available is the trajectory itself. Apollo understood this. The free return trajectory was built into the lunar missions as a form of gravitational insurance. If the main engine failed at the worst possible moment, the spacecraft's path around the moon would carry it automatically back toward Earth, needing only small correction burns. The trajectory itself was the backup. No engine required. Mars has an analog. A Mars free return trajectory is a long-stretched ellipse around the Sun. A spacecraft departs Earth, swings outward toward Mars, passes Mars, possibly without landing, and then continues along the orbital arc and returns to Earth's vicinity roughly 2 years after departure. If main propulsion fails after the initial injection burn, the ship's orbit will carry it home. The source material calls it a cosmic life insurance policy. That is exactly what it is. The orbit itself performs the rescue, but the policy has a premium. A free return capable trajectory is slower and less direct than the absolute fastest option. The launch dates that support the 2-year loop are narrower. Flexibility narrows. Mission speed narrows. The safety built into the orbit costs time. And even in a mission that does not fly a formal free return profile, abort options exist during the early outbound leg. A carefully calculated burn can redirect the spacecraft back toward Earth. Those windows exist, but they do not stay open. As the ship moves outward, gaining distance and velocity aligned increasingly toward Mars rather than Earth, the fuel needed to cancel and reverse grows. Not linearly, sharply. There are specific dates that function like deadlines. Before them, a survivable course change is still possible. After them, the spacecraft is committed to Mars. The window does not close gradually. It closes like a door reaching the end of its frame. The point of no return is a real date on the mission calendar, not a philosophical concept, a specific moment after which returning early becomes, in practical terms, impossible. Every safety measure stacked on top of this adds mass. Extra propellant for emergency burns, redundant life support, heavier shielding for solar storms, backup systems for backup systems. Each kilogram added tightens the rocket equation, because the engines must push more weight for the same velocity change. Fast transit profiles become harder to sustain as the spacecraft grows heavier with safety margins. The more conservative the mission designers choose to be, the further the trajectory drifts from the absolute minimum time option. Time, in this sense, is a risk control knob. A longer mission carries more options. Abort windows stay open longer. Free return opportunities remain in play. More margin exists for problems to be identified and addressed before doors close. A shorter, faster mission compresses all of that. Options disappear sooner. The arrival is more all or nothing. Everything depends on everything else going right. When a mission designer answers the question of how long a crewed Mars mission should take, the real answer underneath the number is a risk tolerance. How much margin do we need before the abort window closes? How violent an entry profile can the landing system and crew survive? What trajectory preserves a gravitational safety net if the engine fails? How much extra mass can the rocket carry while still reaching the required speed? The answers to those questions converge on the same band that the biology, the propulsion physics, and the orbital geometry already produce. The safety architecture does not fight the 6 to 7 month transit. It reinforces it, and the reinforcement runs in every direction. Slower and safer through the cruise, gentler and survivable at arrival, margins preserved throughout. The mission that keeps the crew alive is the mission that takes its time. There is still the question of where that mission lands, and what it finds there. So the mission lands. The 7 minutes of terror end. The heat shield has done its work, the retro rockets have fired, the dust has settled. The crew is on Mars. And then, the orbital clock begins to run. Here is what most people do not fully grasp at this moment. Landing on Mars does not free the crew from the constraints that govern their departure. It deepens them. Earth is still moving. Mars is still moving. Both planets are continuing along their separate paths around the Sun, on their separate schedules, at their separate speeds. Earth completes one orbit in roughly 365 days. Mars takes about 687 days to complete one lap. Those two numbers do not divide cleanly into each other, which means the alignment that made the outbound trip possible is already gone, already dissolving in the rearview mirror of the solar system. And the next favorable alignment is not waiting just around the corner. The crew cannot simply decide to go home. The physics does not allow it. Think about what happens if they try. Attempting an immediate return produces two bad options. The first is to chase Earth on a very high energy trajectory, burning enormous propellant to compensate for the fact that the planets are in the wrong configuration. The second is to accept a bad angle Earth intersection, arriving at a geometry that demands massive correction burns or produces brutal re-entry speeds. Neither option is viable for an early mission. Neither option is even close to viable with the propulsion systems being seriously considered. The only reasonable path is to wait, to stay on the surface of Mars until the planets move back into a configuration that permits a sensible return trajectory, one that keeps propellant demands within achievable limits. That wait is not a few weeks. It is not a few months. The Conjunction-class mission surface stay runs approximately 450 to 500 days. Not 450 to 500 hours. Days. That is longer than a full Martian year, which itself lasts about 687 Earth days. The crew does not merely pass through Mars. They inhabit it. They watch the Martian seasons turn. They see the dust storms build and spread across the surface, sometimes blanketing entire hemispheres. They live through the temperature swings, the shifts in light, the slow progression of a planet that runs on its own calendar. Whatever the habitat and the equipment are capable of handling, they will have to handle it for real. Not in a test chamber, not in a simulation, in the actual environment, over actual time. And here is where the mathematics becomes stark. Even if the outbound and return cruises were instant, even if some perfect propulsion system compressed both flights to zero, the surface stay alone would make the mission roughly 18 months. The approximately 500-day orbital wait does not come from the rocket design or the mission architecture. It comes from the geometry of two planets on incompatible schedules. The flights are not what makes this a multi-year commitment. The wait is. There is an alternative. It has a name. The Opposition-class mission trades the long surface stay for a short one, roughly 30 to 60 days on the surface, then a high-energy return leg that can swing inward past Venus's orbit, on the way back to Earth. Saving roughly 400 days on the surface sounds appealing, but the cost of that trade is steep. The return delta V, the velocity change the spacecraft must execute to reach Earth, climbs sharply. Bigger departure stages are required, either on the surface or assembled in Mars orbit. More fuel must be either shipped in advance or manufactured on Mars. The return trajectory produces higher speeds at Earth re-entry and tighter margins on heating and deceleration. Every part of the system that the long stay approach keeps manageable becomes harder. The opposition-class short stay does not simply shorten the mission, it increases the infrastructure demand, the fuel demand, and the risk profile simultaneously. For early missions, trading 400 days of surface time for that kind of compounding complexity is very difficult to justify. So the crew stays. The question becomes what they actually do with those 500 days. The surface stay is not dead time, it is not a waiting room. The crew is, among other things, a manufacturing operation. In situ resource utilization, called ISRU, is the set of processes by which the mission uses what Mars actually provides, rather than what Earth shipped. Water can be extracted from ice deposits or the ground. That water can be split into oxygen and hydrogen, one for breathing, the other for fuel. The Martian atmosphere, thin as it is mostly carbon dioxide. That carbon dioxide can be harvested and combined with hydrogen to produce methane, which serves as rocket fuel and more oxygen. The propellant for the ascent vehicle, the rocket that will eventually lift the crew off the Martian surface and back toward orbit, does not need to arrive from Earth. It can be staged on the surface, built up gradually across hundreds of days by equipment running around the clock. This matters enormously because every kilogram of propellant not shipped from Earth is a kilogram that does not have to survive the outbound cruise, does not have to be landed safely, and does not drag on the rocket equation all the way from the launch pad in Florida. The crew is also, for the first time in human history, a long-duration physiological experiment at 0.38 g. We have extensive data on what sustained weightlessness does to the human body. We have good data on what full Earth gravity does. What almost no data exists for is what sustained partial gravity, roughly 1/3 of what the body evolved under, does over the course of more than a year. The bones will bear more load than they would in orbit. The cardiovascular system will work somewhat harder, but whether that load is enough to prevent the deconditioning that accumulates over a full duration stay, whether muscles and bones and fluid distribution stabilize or continue to drift, is genuinely unknown. The first crew on Mars will not just be performing science, they will be the science. The data they generate about sustained 0.38 g exposure will define what subsequent missions must prepare for. But there is a dimension of the surface stay that goes beyond the engineering and the biology. It is harder to quantify, and it may be the most significant thing about the entire enterprise. On a lunar mission, if something goes wrong, Earth is within a few days of return. The crews of Apollo understood at a deep level that home was close, not safe in the casual sense, but reachable. The emotional register of that mission, however dangerous, carried a thread back. On the International Space Station, an emergency return in a Soyuz capsule takes hours. The station is, in a meaningful sense, adjacent to Earth. The gap is measurable in minutes to days. On Mars, that thread does not exist. Once the launch window closes after the crew lands, even a perfect ship, a healthy crew, and a fully intact habitat have no physically reasonable way home for many months. Not merely far from home, locked in. The orbital schedule has closed behind them. The next exit is a date on a calendar. It is set by the positions of 2 planets and the geometry of the sun. Nothing the crew does, no decision, no discipline, no urgency, no ingenuity can pull that date forward. It will arrive when the solar system permits it to arrive. Not before. That knowledge changes the character of the entire stay. On Earth deployments, even long and isolated ones, emergency evacuation is possible. The option may be difficult and costly, but it exists as a real thing in the background. On Mars, it does not. Every argument, every mechanical failure, every illness, every moment of doubt or grief or interpersonal fracture sits atop the same fixed fact. There is no quick exit. The safe path home is a date. It is not a decision. It is a consequence of orbital mechanics. The mission does not feel like a long trip. It feels like an entire chapter of a life, because that is what it is. And this is one of the reasons the total duration stays multi-year, even as propulsion continues to improve. A faster rocket can shorten the crew's legs. It cannot shorten the weight. The orbital geometry that traps the crew on the surface for 450 to 500 days does not respond to better engines. It responds only to time, measured against the slow, indifferent turning of two planets on their separate paths. A 3-month transit brings the crew to Mars sooner. They are still there for 500 days before the window opens again. The mission still runs to roughly 2 to 3 years. The years come mostly from the middle, not the ends. What that middle actually looks like for the people living through it, what the body and the mind and the small pressures of a sealed habitat do over the course of that long stay, that question has no completed answer yet. The first mission will begin to answer it, and what it finds there will reshape everything that follows. The middle, though, is only part of what makes the mission feel long. There is something else, something the surface stay does not fully account for. Not the distance itself, but what that distance does to every word the crew sends home and every word sent back. Think about what it means to be unreachable, not cut off entirely. The crew can send messages, they can receive them, but every transmission travels at the fastest speed the universe allows, and even that speed, which feels instantaneous on Earth, takes real minutes to cross the gap between two planets. At the closest point in their orbits, Earth and Mars sit roughly 56 million kilometers apart. A radio signal traveling at the speed of light, 300,000 kilometers every second, takes about 3 minutes to cross that distance one way, 3 minutes to send, 3 minutes for any reply to come back. A simple exchange takes at minimum 6 minutes, and that is under the best possible conditions. But the planets do not stay close. As the mission unfolds, they drift further apart. By the time Earth and Mars reach opposite sides of the Sun, the gap stretches past 400 million kilometers. The signal delay climbs to about 21 minutes one way. A question asked. A 21-minute wait. An answer returned. Another 21-minute wait. A full exchange takes the better part of an hour. There is no live conversation. There never is. There are only messages, sent and received across a gap that grows and shrinks on its own schedule, indifferent to what the crew needs. Now hold that number for a moment. 3 minutes at best, 21 minutes at worst. Those seem like small delays, bearable delays, and in ordinary circumstances, they would be. Something else was happening. The delay is not just an inconvenience, it is a structural feature of the mission. It changes what is possible. When something breaks on the spacecraft, the crew cannot call an engineer and troubleshoot together in real time. They identify the problem, record everything they know about it, and transmit. Then they wait. 6 minutes at minimum before any response arrives, assuming mission control replies immediately. 21 minutes at worst. And in those minutes, the situation continues to evolve. By the time the engineer's advice lands, the crew has already had to act. They are always operating ahead of the advice, not alongside it. They fix the problem, or they manage it, and then they tell Earth what they decided. The loop runs backward. Action comes first. Consultation comes after. For routine operations, this is manageable. Crews train extensively for autonomous decision-making precisely because of this. But in a genuine emergency, those minutes are not small. They are the difference between having a conversation and exchanging reports across a gap that cannot be closed. The speed of light offers a useful way to feel the scale of this. Light travels at roughly 186,000 miles per second. It is the fastest anything in the universe can move. And even at that speed, crossing the Earth-Mars gap takes minutes, which tells you something. The gap is not small. It only seems small on a diagram. Now consider where the spacecraft sits in relation to that speed. A typical 7-month Mars transit covers roughly 480 million kilometers along its curved arc. Divide that distance by the travel time, about 210 days or 18 million seconds, and the ship averages around 27 kilometers per second. In more familiar terms, that is roughly 97,000 kilometers per hour, or about 60,000 miles per hour. By any human standard, that is staggering. A running horse moves at roughly 50 kilometers per hour. The ship is about 2,000 times faster. A passenger jet cruises at around 900 kilometers per hour. The ship is more than 100 times faster than that. There is nothing in ordinary human experience that moves the way this spacecraft moves. And yet, at 27 kilometers per second, the ship is traveling at roughly 0.009% of the speed of light, less than 1/100th of 1%. Light is approximately 11,000 times faster than the spacecraft. That is why light crosses the Earth-Mars gap in minutes, while the ship grinds through the same geometry over months. Both are moving. The difference in what they can do with that distance is almost incomprehensible. Two truths sit together here, not in contradiction, but in a kind of permanent tension. The ship is moving faster than any vehicle humans have ever ridden in the history of our species. And on the cosmic scale, it is barely moving at all. Some people hear that and assume there must be a workaround. At these speeds, does time not compress? Does relativistic time dilation not change the experience of the journey? The answer is no. Not at 0.009% of light speed. Time dilation becomes meaningful only at very high fractions of light speed. Somewhere around 10%, 50%, 90% of c. At those velocities, time genuinely stretches and compresses. A 2-year trip could feel like weeks. Physics allows it. But 0.009% is nowhere near that territory. The effect at ship speed is so small, it cannot be detected by any instrument on board, let alone felt. A 2.5-year mission is 2.5 years. For the crew, for their families, for everyone. The bodies and the calendars age at exactly the same rate. There is no shortcut through time. No return home to find the world has moved on and the crew has barely aged. The years pass at the same rate on both sides of the gap. That is one of the harder truths of the physics. The emotional texture of the communication delay runs deeper than operational risk. Think about what it means to receive a message that is already old. A voice recording from a parent, a partner, a child, sent days ago, arriving now. The words describe a moment that has already passed. The person who recorded it has already moved on from whatever they were describing. The reply the crew sends back will arrive equally old. There are no conversations on a Mars mission. There are only exchanges, each one a fragment from a different moment, stitched together into something that resembles a relationship, but runs at a different pace than any relationship either side has ever experienced. A letter is a reasonable analogy, but only partially. The closest equivalent might be a correspondence where every letter arrives after the news it contains has already changed, and every reply arrives after the question that prompted it has already been decided one way or another. Not slow conversation, something different in kind. The crew learns to hold both realities at once, the connection that still exists and the gap that never closes. This is one of the reasons the mission feels longer than its numbers suggest. The distance is already extreme. The communication delay makes it more extreme in a different dimension. The kilometers separate the body. The lag separates the voice. Together they produce an isolation that no amount of training fully prepares a person for, only experience does. And that experience has never been accumulated on a mission this far from Earth. Not yet. So the question becomes, what could actually change? The isolation will not shrink. The orbital lock will not dissolve. The surface stay will not compress because a better engine arrives. But the cruise legs, those two arcs of empty space between the planets, are the one part of the mission that propulsion can genuinely reshape. The question is, by how much? And the honest answer is, more than people expect and less than people hope. Start with the most likely near-term scenario. The first crewed Mars missions will almost certainly still rely on chemical propulsion. Methane and oxygen, or hydrogen and oxygen. The chemistry sets a ceiling on how fast the exhaust leaves the nozzle, and that ceiling is roughly 3 to 4 kilometers per second. Nothing about building a larger or more refined chemical engine changes that number. The fuel itself is the constraint, but there is room to maneuver within that constraint. With a favorable launch window, an orbital refueling strategy so the ship departs Earth orbit fully loaded, rather than carrying the extra mass of propellant through the climb out of the atmosphere, and a higher energy trajectory that trades fuel efficiency for speed, a one-way crew transit can push into the 3-month band. 90 to 120 days, one way. That is not science fiction. That is hard engineering, requiring multiple launches to fill orbital depots or Starship-class vehicles, before the crew departs, more propellant burned overall, and a sharper arrival geometry at Mars. The cost is real, but the physics is not speculative. Early missions may keep the crew on the more conservative 6-month path and send cargo ahead on the slower, cheaper lanes. The crew follows when the infrastructure is in place. The picture did not hold. Even reaching the 3-month transit does not fundamentally change what was described in earlier sections about the mission's shape. It changes the crews. It does not change the mission. The next step up is nuclear thermal propulsion. A reactor heats liquid hydrogen to extreme temperatures and expels it through a nozzle. No combustion. The exhaust velocity roughly doubles compared to chemical engines, which matters more than it sounds because of the exponential mathematics of the rocket equation. With nuclear thermal stages on the interplanetary legs, transit times of 2 to 4 months become achievable without the propellant mass spiraling into an unworkable ratio. 2 months is the ambitious edge of that range. 4 months is the relaxed target. Nuclear thermal propulsion has never flown in space, but the physics is well understood, validated by the NERVA program in the 1960s. The engineering challenges are real. Reactor reliability across the cold vacuum of deep space, radiation management, the difficulty of launching nuclear material through Earth's atmosphere. None of these are trivial, but the concept is not distant speculation. Beyond nuclear thermal, there is a class of propulsion that moves into different territory entirely. Continuous thrust drives, engines that do not burn briefly and coast, the way every mission to Mars has ever worked, but instead push the spacecraft steadily for weeks. Even an acceleration of 0.001 g, which is roughly a tenth of a meter per second, sustained long enough, allows a completely different mission profile. The spacecraft accelerates for the first half of the journey, flips, and decelerates for the second half. Under that kind of profile, the cruise to Mars would compress from months toward many days. It would also give the crew a small but continuous sense of weight, a gentle pull toward the floor, not enough to fully replace Earth gravity, but enough to ease some of the physiological costs of weightlessness. The catch is the power source. Continuous thrust for weeks requires either a very advanced nuclear reactor or a fusion drive producing thrust with exhaust velocities far beyond anything nuclear thermal can deliver. No close prototype exists today. The gap between the physical concept and a working engine is measured in decades, not years. So the realistic ladder runs from roughly 6 months with current chemical propulsion down to 3 to 4 months with high-energy chemical and orbital refueling, down further to 2 to 4 months with nuclear thermal, and eventually in some future that cannot yet be scheduled, perhaps to weeks with continuous thrust technology. That is a genuine compression. The question is whether it changes the mission's total duration in any meaningful way. This is where the math reasserts itself, and this is the reveal that tends to surprise people. Pull up the numbers. Even in the most aggressive realistic near-term scenario, with a 90-day outbound leg and a 90-day return leg, the surface stay remains what it always was, 400 to 500 days. Orbital geometry sets that number. Better engines do not move it. The crew still waits on Mars for the next viable return window, still inhabits a full Martian year, still accumulates the biology of low gravity across the same span of time. A total mission under that aggressive transit profile runs roughly 1.5 to 2 years. A more conservative first-generation mission, with 6-month cruise legs on either side, runs 2.5 to 2 8/10 years. Not a quick trip, not a semester and back. The cruise is compressed. The mission is not. There is another layer to this that the numbers alone do not show. Below roughly 3 months per cruise leg, further compression produces diminishing biological returns. The biggest gains in crew health and mission psychology come from the long reductions. 9 months down to 6, 6 down to 3. Those cuts meaningfully reduce radiation accumulation, slow the rate of bone and muscle loss, and shorten the period of total sensory confinement. But once a transit is already at 3 months, shaving it to 2.5, or to 60 days, or to 45 days, produces smaller and smaller improvements in crew health, while the engineering cost keeps climbing. It is like squeezing water from a nearly dry towel. The first squeeze gives a lot. The 10th squeeze barely produces a drop, and the effort becomes significant. At some point, mission planners may deliberately stop short of the physical minimum transit time, not because they cannot go faster, but because the biological gain no longer justifies the added mass, complexity, and risk. The sweet spot is the point where the transit is fast enough for crew health and morale, but not so fast that it demands engineering margins that squeeze everything else. That sweet spot, by most current estimates, sits around 3 to 4 months each way. There is a cultural dimension to this as well, one that the numbers alone cannot fully convey. A 3-month transit to Mars is still a long way from home, but for a generation of people who grew up in a world where Mars missions are ordinary, where spacefaring is part of the understood landscape of human life, 3 months may carry a different weight than it carries today. A semester abroad, an extended deployment, a working season in a remote place. Not comfortable, not brief, but normal. Something that fits into a life plan rather than consuming it entirely. But here is the pattern that technology cannot dissolve. Better engines move the transit. They do not move the totals. The full calendar still reads, roughly 3 months out, roughly 400 to 500 days on the surface, roughly 3 months back. Even the most optimistic near-term futures produce a mission measured in years. The crew's legs compress. The orbital geometry and the biology set a floor underneath them that no rocket equation can cross. Technology bends the timeline. The combination of orbits, human limits, and mission requirements keeps pulling the total back into the same shape. Not the exact same numbers, the same fundamental form, multi-year, life reshaping. The kind of commitment that is not a long journey, but an era. And that floor is only the physical minimum. What actually happens on the surface once the crew arrives, and what the mission demands of people in those 400 days far from any exit, is where the true weight of this commitment becomes clear. So draw the honest calendar, not the slide deck version, the real one. A first-generation mission, built on the best chemical propulsion available today, looks like this. Outbound cruise, roughly 180 to 210 days. Surface stay, roughly 450 to 500 days. Return cruise, roughly 180 to 210 days again. Added up, you get somewhere between 900 and 1,000 days. Between 2.5 and 2.8 Earth years physically off the planet. That is before the years of training on the ground, before the months of rehabilitation after return. Just the mission itself, nearly 1,000 days. Now apply more aggressive propulsion. Starship-class chemical with orbital refueling, or an early nuclear thermal stage. The crew's legs compress. Outbound drops toward 90 to 120 days. Return the same. But one part does not move. The surface stay is still 400 to 500 days. The synodic cycle does not care what engine you use to get there. The total mission in this more advanced scenario runs roughly 1.5 to 2 years. Better. Still years. Why can the total not shrink to 6 months? Why does that number keep reasserting itself, no matter how the engineering improves? There are 3 answers, and none of them negotiate. First, orbital alignment. Earth and Mars come into favorable geometry on a roughly 26-month cycle. That cycle is a product of the 2 planets' orbital periods. It is not a schedule anyone chose. It ran before any mission was proposed. It will run long after the last mission returns. You cannot move the departure window with a bigger engine any more than you can move a tide with a bigger bucket. Second, radiation and microgravity together impose a survivable band on the transit itself. Slow down the cruise, and radiation accumulates to dangerous levels while the body deconditions. Speed up too aggressively, and the arrival kinetic energy becomes brutal, entry G loads threaten the crew, and the engineering margins collapse. The band that keeps the crew intact, outbound and back, is measured in months, not weeks. The physics that define the lower edge of that band and the upper edge point to the same answer regardless of which side you approach from. A few months each way, no shorter, no longer without compounding costs that rapidly outweigh the time saved. Third, the mission itself requires the surface stay. Understanding how human bodies respond to 0.38 G over the timescale of a year requires staying for that timescale, testing systems, generating data. One quick in and out visit would teach almost nothing about whether people can function on Mars over the long term, and the orbital geometry that permits those hops demands a completely different, far more propellant-intensive architecture. The science and the safety logic both push toward one large, well-planned expedition with a stable surface phase, not repeated short sprints. But what if propulsion could be pushed further than nuclear thermal? What if the crews were brought down not to weeks but to days? This is where the physics gets genuinely strange. Imagine continuous 1G acceleration throughout the trip. Not a brief burn and a coast. Constant thrust, giving the crew a steady sense of weight the entire way. Something like a long elevator ride through space, the floor pressing against your feet, even in the void between planets. At 1G, speed builds at roughly 10 meters per second every second. After an hour, the ship is moving at tens of thousands of kilometers per hour. After a day, thousands of kilometers per second. At that point, Mars's distance of roughly 56 million kilometers at closest approach starts to feel small. Days instead of months. Then the data shifted. At thousands of kilometers per second, relativity begins to matter. Small twin paradox effects, measurable differences between clocks on the ship and clocks on Earth, start to enter the calculation. The physics of the journey is no longer purely Newtonian, and the propulsion requirements become almost incomprehensible. The specific impulse needed for continuous 1G thrust through an interplanetary voyage is so far beyond chemical or basic nuclear thermal that those engines look like toys by comparison. You need fusion drives, or matter-antimatter propulsion. Each kilogram of fuel carrying energy comparable to a nuclear weapon, fed steadily into an engine for days on end. No such engine exists. No prototype exists. The gap between where propulsion science sits now and where it would need to sit for this scenario is not a gap of a decade. It is not clear it is a gap of a century. And there is another problem, a quieter one, that does not appear on most lists. Interplanetary space is not empty. There is dust. At the speeds a spacecraft normally travels, hitting a grain of that dust is a small tap, mechanically trivial. At thousands of kilometers per second, each grain hits with the energy of a bomb. The ship would need either exotic armor or active protection systems capable of deflecting particles at those speeds. Both add mass. More mass requires more propulsion. More propulsion raises the energy requirements further. The problem is not linear. It spirals. What about not going faster at all, but going around the distance entirely? Warp drives, wormholes, the concepts have names. The Alcubierre warp concept compresses space in front of the ship and expands it behind, so the ship rides a bubble of distorted space-time without moving through it locally at superluminal speed. Wormholes tunnel through space-time, connecting two distant points so the effective distance between them becomes negligible. Neither approach requires breaking the local speed of light. Both approaches require exotic matter, a form of matter with negative energy density, never observed in usable form. Every version of these concepts examined seriously by physicists runs into either energy conditions in general relativity that appear to rule them out, or quantum effects that make the structures unstable, or energy requirements so enormous they become meaningless as engineering targets. This is not a statement that Mars in days is ruled out forever by physics. It is a statement that the gap between what can be built and what would be required is enormous. In any realistic future, even an optimistic one, even one with cheap launches and routine nuclear stages and early continuous thrust systems, a person going to Mars lives on Mars time, not Earth weekends, seasons, years. The trip becomes shorter and safer. It does not become a quick getaway. So translate all of this into a life. Before launch, years of training, physical conditioning that would challenge professional athletes, engineering drills, emergency simulations covering every failure mode the mission designers could anticipate, geology, systems, medicine, Procedures. Psychological screening. Years. The launch pad is not the beginning of the commitment. It is the moment the commitment that began years earlier becomes visible. The mission itself, somewhere between 1.5 and 2 years in an aggressive high-energy architecture, and between 2.5 and 2.8 years in a conservative first-generation profile, physically absent from Earth for all of it. After return, months of rehabilitation, muscle and bone rebuilt against full Earth gravity after a long stay at 0.38 G. The cardiovascular system adjusted. The nervous system recalibrated. The psychological weight of isolation, of risk held continuously, of returning to a world that moved while you were locked in place, processed gradually over time. The medical file watched for the rest of a life. Radiation exposure that represents a non-trivial fraction of a career limit, accumulated in a single mission. The mission does not sit inside a life. It rewires the life. Now step back one more time and hold the full picture. Mars is close. In cosmic terms, it is the very next destination outward. At closest approach, roughly 56 million kilometers away. Not billions, not light years, the next planet. And reaching it, landing humans there and bringing them home safely requires multi-year plans, precise orbital choreography, choreographed around a 26-month cycle, no engineer designed, life support systems operating without failure for thousands of hours, vehicles performing at the edge of what current engineering can build, and crews willing to accept that no early exit exists once the surface window closes. If this is the cost of the nearest planet, then the real scale of everything beyond it begins to come into focus. Not just as a number, as a way of thinking. Becoming a multi-planetary species is not simply a matter of building a better rocket. The rocket matters. The propulsion matters. But the deeper change is in how long a plan is allowed to run. A Mars mission does not fit into a quarterly schedule, a fiscal year, or a 5-year program review. It fits into the timescale of planetary orbits, biological generations, and institutional patience measured in decades. The honest answer to the question of how long it takes to reach Mars and return has never been a number of months. It has always been a chunk of a biography, a rearrangement of a life around planetary time, a commitment to the logic of orbits and human bodies and mission requirements that produces, in every realistic scenario, a total measured in years rather than seasons, and seasons rather than weeks. Not a long flight, not a voyage, a chapter, written in the language of orbital mechanics and human physiology, on a timeline set not by any mission planner or any rocket engineer, but by the slow, indifferent turning of 2 planets around the same star.